Okay. Hello everyone, it's June 18th. Morning session. Fresh mind. Let's get to it. Anything need to take care of? Nope. Alright, let's do this. Range sum query. Mutable. Range sum. Ooh. Okay. Given an integer array nums, handle multiple queries of the following type. Update the value of an element in nums. Calculate the sum of the elements of nums between indices left and right, inclusive, where left smaller equal to right. Implement the numArray class. We have initializing, void. I want to update the value. Range sum, return sum of the elements of nums between indices left and right, inclusive. This is segment tree, right? It's no question about it. The segment tree is used to handle exactly this situation. So there's nothing special, I think, right? Nothing special. It's just going to be asking you to implement a segment tree. Do I know how to do segment tree? I think I read it the other day, but I don't have the best clue, but I can try. Can definitely try to do it myself. If it gets too hairy, then most likely that means I was wrong. Yeah, it doesn't really matter. This is a segment tree. Segment tree, I think it took what, OON to set up, and it takes O log n to update and O log n to query. Yeah. All right. Segment tree. Indices. Remember, let's keep the indices inclusive on the left side and not inclusive on the right side. Okay, so let's give this example. 135, right? 135, well, 135. So that one is segment will be 0, right? 0 to 0, 1, 2, 0 to 2. Oh, yeah, it's inclusive on the right side. It should be 0 to 3 if we want to do not inclusive. One of them cannot be inclusive. The left subtree or the right subtree. I forgot. How do we reconcile that? If on the right side is always not inclusive, we can try that. We say on the right side is not inclusive, then it's not 0 to 2, it's 0 to 3. Right? This is 0 to 3. So on the right side is not inclusive. And we can compute the sum, right? No, the sum is a compute at the end. So 0 to 3, and then we're going to split, right? Split. So on the left subtree, it's going to be 0 to 2, 2 not inclusive. On the right subtree, it's going to be 2 to 3, right? And then on the left subtree, we keep splitting. It's going to be 0 to 1, and then 1 to 2, right? 1 to 2, and the right subtree is already ending. So once we reach the end, we put the numbers there. So 1 and 3. Then we go back, we add them together, it'll be 4. 2 to 3 is 5, and then the top is 9. Okay, so that's the segment tree. Now we want to query 0 to 2. So we want, and 0 to 2 is inclusive, I think, when you do the query between indices left and right. So it's inclusive. So when we query, we have to query 0 to 3. Right, because our range on the right side is exclusive, so 0, 3. And 0, 3, it's the top one, so return 9. right? And then we're gonna update indices 1 and 2. So we go indices 1, 1 go to the left subtree, 1 go to the right, right? So because we have to go to 1, 2, so go to here, and then we update 3 and update to 2. Once we update, we need to track him back. How do we track back? I think to track back, isn't like every single one we have to track. Like 9, we have to know original value is something, and then we need to change. Yeah, along the way, right? Along the way, we make changes, right? So we know it's 3, and then we need to change it to 2, so we have a delta, right? Delta is going to be plus 2 minus 3, so it's minus 1. So when we return back, it's going to be 3. Return back, it's going to be 8, right? So we update it, and then next one we'll query 0 to 2 again and become 8. Let's try it. Let's try it. I mean, I think we can get it. We can get it. I mean, I haven't considered any edge cases, but that shall be fine. Right. Let's take a look. All right. Segment tree. Can we use like left and right? Let's just create a new node. Just to make it easier. Right. So we say class tree node. Right. Tree node. Def initiate self. Or what do we have? Tree node we have a sum. Right. We have a sum. The value is. Let's not do this. Let's just say it's gonna be nothing. And under range, right? Range. So left is gonna int, right, int, right? And then we also make sure we're gonna say left. The range is we include left but exclude right. So this is going to be this. Self.left equals left. Self.right equals right. And self.sum equals, I don't even know what it is equal to. Equals to none. Let's just equal to none. It doesn't really matter, honestly. Yeah, we can put anything in it. So we can just put sum here. Sum. Right? But I think sum is a function, so I don't like to do it that way. So range sum, right? Range sum. Yeah, let's call it range sum. Range sum. Too many words. R sum. R sum, right? R sum representing range sum, and then this one, let's change it to R sum. Okay. Oh, hold on. Left and right will also be child. Okay, so left, range left, right? Range left, range right. So range left, range right, and then self.left equals none. Self.right equals none. Right? Range left. That looks too similar. I don't like it. Let's put an underscore. Let's put an underscore. I think it's necessary. Put an underscore to make sure, and also range sum. We're gonna do underscore as well. R underscore sum. Okay, so that is the tree node. Okay. So we initialize it. We need to create So we can say self dot segment tree equals self dot make seg tree, right? So make seg tree, we're gonna pass in nums. So we need to create a function, call it def make seg tree self nums. All right, now we need to create one to return internet. Come on, internet. There we go. We're back online. All right. Nice. Of course, we're gonna do self.nums equals nums. I don't have to pass nums, but we can do a 0 and len nums, right? So we get that. So instead of do this, we're just gonna say range left int, range right int, and then also again we do not include right. So we're gonna create a new node. We say if range left plus 1 equals range right. That means we are at the leaf node. Then we're just gonna return a tree node with range left, range right, and self.num range left. That's it. Else, then we are inside. Else, then we're gonna do what do we do else? Else, we're gonna say root equals tree node. Same thing with the range left, range right, and value we just put a 0 for now. Actually, let's do this one equals a 0. Yeah, it's fine, equals 0, so I don't have to put this. And then this one has to say r sum equals, right? So we do a root, and then we say root, let's say left equals self.make segment tree, range left, right? And then range left plus range right, range left plus range right divided by 2, right? So that's the left subtree, and then we do the same thing with the right. I should just say root dot left, root dot right, and root dot right is going to be this and range right. And once we're done, we say root dot r sum range sum equals root dot left dot r sum plus root dot right dot r sum. Once we're done, we return root. Right, so that is that is the thing. That's to make the segment tree. Okay, so now we've done the segment tree. That is it. Now we're gonna do update, right? Update. Update will be, we have the index, so we try to see which side we need to be on, right? So we need to do a what? I mean, we already know for sure. Oh yeah, because we have nums, right? So we know the, how should I say it? We know the delta. We know the delta. So we can just traverse through the tree and then change the value, right? So we can just say we know delta equal to value minus self.nums index, right? We know this. So first of all, oh yeah, that's delta, and then we say self.nums index equals value, right? So we update that. Now we're gonna update the tree. So what should I do? What should I do? It's going to be a recursion as well. So we say def update, and then make another function here to say def update segment tree, right? So what we need is self root is going to be tree node, and delta can be int, right? Yeah, and then this one will return none. But honestly, no, we do need that. Do we need that? I'm trying to see if it's possible that we don't need to involve nums at all. Segment tree. I mean, we can return the delta, right? We can return the delta. So we can return the delta, which means root, I don't have to pass delta, but I need to pass the index, right? I need to pass the index, right? So when we hit a node whose, so we say if root dot range left plus 1 equals root dot range right, that means we're at the leaf, right? Now we say root delta equals root dot rsum. Actually, it's going to be, oh, have index and we need to have the value. Ah, isn't this? But we need to pass the root. That's why. Update. Can we use this? But how do you handle the root? We're going to pass a new root. This one doesn't have a root. No, I like this way. It's clearer, right? So index value, right? So we say delta equals val minus this, right? And then we say, actually, then we say root dot rsum equals val and return delta, right? Return delta. Now for all the others, we're gonna say delta equals what? Equals update segment tree. Update segment tree either root dot index and val, right? If index is inside root dot range left smaller equal to index smaller than root dot range left plus root dot range right divided by 2. Now let's look. It's too long. I don't like it. It's too long. Let's do it this way. If this, then we just say root. Yeah, we need to have delta. Delta equals this, right? Else delta equals, I'm going to go to the right subtree. Go to the right. Right? And then once it's done, we say root dot rsum plus equal to delta and return delta, return the same delta up. So that's update segment tree. So what we're gonna do is We don't have to do this. We just update the nums. But actually, we don't need to update the nums, right? We don't need to update the nums. So we don't have to keep this. It only used in the first time. Which honestly, if you think about it, we can just pass it down. Yeah, we only need to use it once. So let's just put it inside and then nums, right, list int, and we just, when we call it, we put the nums in here. Yeah, and then it's not going to be self.nums. All the self.nums going to be nums. Oh, I want to use it once. So be nums. So we don't need this. And we certainly don't need this. We can just call it self.update segment tree. Self.seg tree. That's a root, index, and a value. Right? So one call here. Some range, I'm going to query it. Right? Query it. Some range, we're going to query it. So the query is going to give us a range, right? And then we're going to go to the left. Oh, I think we might still need it. No, I don't think so. Hold on, let's query it. Let's query it. Let's query if something in a range, right? If it's like in the middle, like one is in the middle, one is in the right. How do we do it? So we have the middles, we split into two, and then we keep going. Eventually we'll reach a range that gives us the value, and then we just return that value up. And that will reach a value, and then we return that value up. That shall do, right? That shall do. Yeah, I think that shall do. So some range. Maybe we can. Hold on. I think we can do. We need to have the root. Same thing, right? Same thing. So I want to just do another one here. Def query. Query segment tree. Right, some segment tree. Some seg tree. Self, right? Self root is going to be a tree node. And we have left int, right int. Oh, I feel like I have done this before. I have a bit deja vu here. Alright, so some segment tree. So we have the root, and we're going to say mid equals root root dot range, left plus root dot range, right divided by 2, that's mid, right? And then we can say if left is smaller than mid, then we have to check if right is small. So we have right smaller than mid, left larger or equal to mid, and or the third case, which is the mid is in between, right? We have 3 cases, and each case will give us different result. So we say if left, right? If left If left is larger or equal to mid, right? Then we're gonna sum segment tree root dot right, left, and right, and we get a value out. We're gonna figure that out later. So if right is smaller than mid, right? Then we say, what if right is mid? And right is mid, we have to split. Okay, so sum segment tree root dot left, left and right. Else, then we have to split. How do we split? We're gonna split into sum seg tree root dot left. What is the range? The left to mid, right? And it's the plus sum. It's gonna be root dot right, right, mid to right, right? That's if right equals mid. What if right equals mid? If right equals mid, then it's going to be by itself. Oh, hold on, the query. The query, we have the plus one. Yeah, right is always plus one. So it won't happen. Right is not gonna equal to, hold a sec. So we're passing left and right? What if, so that's 2. What if we do 0, 2? 0, 2, 0, 2. So I think it's right smaller or equal to mid. Right? Right, if it's smaller or equal to mid, and if right is not inclusive, and it's smaller or equal, then we go to the right and to the left. The right is larger than mid. Right is larger than mid. And the left is larger or equal to mid. Yeah, I think it's this, right? And then actually call it. I'm going to just say return self dot sum seg tree left right plus 1. I have to do plus 1 here. So we're not done yet, right? So this one give us a value which we can return, no problem. This one give us a value we can return, no problem. This one we're gonna return this plus this, no problem. And what we need is the end case, the anchor case. What is the anchor case? Well, the anchor case is go left to mid. Anchor case is if root dot left, root dot range left, right, equals left, and root dot range right equals right. And then one time this will happen, right? When this happens, we're just gonna return root dot r sum. Otherwise, we do all this, and that's our solution. We're gonna put in the test, not with ours, but with this, and just see if it works. Okay, let's try it. Run code. Name NU is not defined. I probably have a typo. Where? Root.right self make segment tree. Ah, nums. Try it again. Second tree missing position argument right, where return self dot make self dot make segment tree. No, not that one. Which one? Sum segment tree. Sum root left right. Sum, oh, I forgot the root. Self dot seg tree. Okay. Ending, judging. Name update second tree is not defined. I kept forgetting stuff. All of these. Oh my god. Alright, I need to copy and paste back in here. That's terrible. We forgot a self. Is self dot. And all the sum segment tree needs to have self as well. Okay. Now let's do it again. Alright. Run again. Pending. Judging. Finished. Alright, it looks good. Let's give us more shot. Alright, we got more values. And range 0, 1, 1. Update range is 0, not 0, 1. 0, like say 0, 8. And then I'm going to change it to 100. And then we query another one, let's say 1 to 9. Should I do a couple more queries? Let's do a couple more queries. Let's do query 1, 2, right? And then we can do a query 3, 5, 3, 6, right? Then we do a update 6, update to 1000, right? Then we say some range, some range, some range, some range, to some range, and when you do an update, I say one more some range. All right, let's take a look on this one. Length of methods must be the same as param. I think I messed up. Some range, update, some range, some range, some range, update. We need a one more. Let's do 8 to 10. Do I have 10? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Number 13. Number 13. Alright. If this pat, God. Oh, there's a limit. Yeah. I didn't know. Minus 50. How about that? Yeah, looks good. I have one more thing I want to do, which is 1. Right? I'm going to do 1. So some range. So it's going to be 1. And then it's going to be range. That has to be 0 to 0. Right? And then we update 0 to 2. Then the only thing we can do is 0, 0. And then we only need 3. So I'm going to remove the rest. Not necessary. That's going to be the last test case I'm going to try before we go for it. Alright, that's the last test case. Alright, let's go for it. Submit. Pending. Judging. That's so slow, but we did pass. It's much slower than I had expected. Okay, I mean, we passed, but why is it so slow? 2,988 milliseconds. I do not know. think I changed something, so I have to copy and paste again, just in case I did change something. Okay, so I think this is the correct version. Is there a better way to do this other than segment tree? I don't know. I honestly have no idea. Anyway, so we can just write it. Where do we write it? Right here. Nothing fancy, just a practice, practice of building a segment tree from scratch. The initialization is on to build a tree. Update and sum range are both O login. Yeah, I think this is reasonable, and we hit a bad runtime actually, not too good. 2988 milliseconds. 2988 milliseconds with 42. That's like regular, right? Like regular play. 42%. All right, let's take a look. What is the smart people going to do with this? Yeah, it's a medium question. No doubt, LeetCode. I mean, this is like if you know what they're looking for, it's straightforward. If you don't, you might sweat a lot. It's submission. Yeah, I haven't done this before. It's the first time. Date, solution, naive. Time compare on minus function query. What's RSQ? Range sum query. Let's just take a look. So sum, the sum up, return, on for each one, and O1 for this. Time compare on, O1, but time limit exceeded. Okay, range sum query, that's what this means, range sum query. Oh, this is accepted. Segment tree. To build. Query, this is so much easier, right? Login, this is also login, I think. Yeah. Okay, so what is this? Sqrt Decomposition. Split array in blocks with length of Sqrt n, then we calculate the sum of each block and store in an auxiliary memory. It will add the sums of all the blocks lying inside and those that partially overlap with the range I to j. 9, which is split into blocks of size 3. To get 1 to 7, we add b1. Stores the range and partially sums the block b0 and block 2, which are overlapping boundary blocks. Now, it's definitely a segment tree, no question about it. So the way that they implemented 0, 3, 0, 1, and 2, 3, so there's no overlapping. Maybe that is the key. Don't overlap. Mine overlaps. So divide by 2, and divide by 2 plus 1. Interesting. So the building part, I think, is the same, right? Nums.length larger than 0, and then equals this, tree equals new. Ooh, look at this. The implementation is just an array. Because it's a complete, no, what's that? A complete, yeah, is that complete binary tree? So it's possible to use, hold a sec, that is interesting. That's the overhead. That's the overhead that's causing the issue. And n equals this, tree equals new int n times 2. Yeah, n nodes times 2. That's a complete binary tree. And we're gonna build a tree. Ooh, what is this? Tree equals, this is the left, this is the right, because it's a 0 based, right? So it's a right tree, left tree, right tree. And for I is n, j is 0, I smaller than this, I plus j plus tree I equals nums j. What is this magic? Oh, we begin from the leaves. Ah, yeah, you can access the leaves. Leaves. J is iterating from the nums. I is the leaves. Yeah, because it's a full binary tree, so you can do this. Ah, I learned something new about segment tree. Yes, you can do it that way. So that's to fill in up the leaves. After you fill up the leaves, you can, from -1, and then you just add them together. Okay, okay, fair enough, fair enough. How do we know the range then? Bottom up to build some tree. Know from the above that if some node P holds the sum of range, its left and right child hold the sum of, yeah, that's true. To find the sum of node P, we need to calculate the sum of its left and right in advance. We begin from the leaf, initializing everything, then we move upward to get it. Okay, so how do we know the range? You have position 0, right? And then I know my left and the right child's positions, but what I do not know is the range they represent. Let's move on. Let's see how they find it. All right, update. Position plus. No way. Ah, we always. Oh my god. That is correct. We go from bottom up. We go there, right? We go there, and we find the value. So that's the one we update, right? After we update it, we bubble up. Why we bubble up? So initially left and right is this position, and then We just need to find its parent. Hold on, actually I don't know. Let's keep looking. Let's keep reading. So left is position, right is position, right? So this is the current position. And then position, if position is even or odd, well, that's because left child is always even and right child is always odd. So if it's even, then the other child is me plus 1. If it's odd, the other child is me minus 1. If it's even, right is this. If it's odd, left is this. Then we update the parent. Oh, bravo, bravo, bravo. Ay, muy bueno. Muy, muy bueno. See, position, we divide by 2. That gives us the parent. Parent gets updated. And then we go from parent. Oh, wow. Very good implementation. All right, how about the range sum? Can you do it yourself? Okay, let me try to think about it. So we have LR, right? I have a left and right. Actually, I still don't. Oh, yes, I know. We have left and right. So we find the leaf, right? We go to the leaf. So we know the leaf, the leftmost leaf, the rightmost leaf. So we find those, right? And then we bubble up. So we know that's the left. So we find its parent. And then we find on the right side its parent. And then we keep finding the parent, until the parent is the same. Nope, 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 nope. We'll have the left child, the left tree, the left leaf, right? And then if we go 1 up, right? And right we can go 1 up. But yeah, eventually we will, right? Well, we will reach the top if it's the left and right. What is complicated if the left, the L, the left, right, if this L is actually a right leaf, right? When that happens, what do we do? If it's a right leaf, then we know the value needs to be changed. Yeah, because this is saying this to this, right? And then when we update going up, it needs to be, we need to remove the left, right? We need to remove that part. So I will be different. Hold on, hold on. Go down, and then we're at the leaf level, right? If the leaf is a left leaf, that is simple. That is simple. So we just go all the way up, and then we're good. If the leaf is a right leaf, for the L, right? If a leaf is a right leaf, then when we go up, we cannot use that because that includes both. So we have to go up with the right value up, right? And then at each position, yes, I think it's at each position we need to check. At each position we check if it's a left or a right. If it's on the left side, right? If it's on the left side, if it's a right child, then we have to return. Oh wow, it's actually not straightforward as I thought. Is it right? If it's on the left side, if on the left side we have a left parent, we have the right parent, right? We have 2, and then eventually we'll bubble up towards the same value, but we'll carry something when we return. So if it's on the left side and the position is on the right position, then what we need is to find the left one and like minus the left one, right? So when we return, we're going to have to return minus the left one. So we're here, right? And when I return what? I know my parent contains both of us, but that is not good because I cannot let it contain both of us. So I need to return like minus the child that's not included, right? And the minus a child that does not include. So instead of 3, like in this, I'm looking at the original tree, I need to return a -1, right? A -1, and that is a left child, so we can just not minus again. So we have to have something like minus at every level up until we map. I want to try this. I don't want to see it. Right? I don't want to see it. I try to implement all by myself. But I feel like the actual solution will have something smart. But give it a shot. So we're gonna say self.secTree is going to be 0 times 2 times len nums, right? That's a secTree. Now we're gonna build. Nope, no, not here. Def make secTree self nums. Nums is a list of integers, and this one gonna return nothing. Right. So all we do is first we fill in all the leaves. So I say for I in range, we can just say n equals len nums, right? So I in range n, right? Say self.secTree I plus n equals nums. Actually, I can do even better. I can just say I n enumerate nums, so I don't need to have this, and this one equals n, right? So that is first one. We get the leaf done. Now we want to get a parent done as well. So to get a parent, so each parent, right? So it's going to be for j in range. It's going to be n-1, right? Yeah, it's going to be n-1 to 0. J is a parent, so we say self.secTree j equals self.secTree 2 times j was 0 based plus self.sec3 2 times j plus 1. Right? That's it. So we say, I see. This has to return a list of int. This is not going to be here. This is going to be here. So sec3 equals this, and all the self dot is not necessary. And then we just return. We return sec3. So this one equals self dot make sec3 nuns. Right? Now update. Update is going to be let me say self dot n equals len nuns. This one is useful. This one is not, so have to self dot n. Right? So we're gonna first update self.sec3 index plus n. Yeah, follow position equals index plus n plus self.n. Then this is going to be position equals value. And then we say what? While position. If I have a right, I have a parent, right? So I'm going to say while, but we have to update the parent as well. And then we say position, going to divide it by 2. I'm going to go to parent, and parent is 0. So I think it should be while true, right? And we have the position right now, so we need to find its left and its right. So we're going to say left equals position, left equals right equals position. And say if position is an odd, that means on the right, I'm on the right, so we say left minus equal to 1, right? Else I am the right, so right equals right plus equal to 1. So I have left and right ready. When I have left and right ready, when I say parent is position equals I have left and right position divided equal to 2. That's my parent. So we say self.sec3 position equals what? Self.sec3 left plus self.sec3 right. Then end position is if position is over 2, the kind of parent done, and then so we can while position. Yeah, while position. Then we do this. Done. Right? That's update. Now sum range. So we start from the leaf, right? We start from the leaf. We need to go all the way up, trying to find. Like if from the 2 we start searching, going up, right? From the 2 we start searching, going up, and eventually they will merge. They will meet each other, right? They will meet each other. So we just need to keep track during this path how much value we need to remove, right? So we have a left and we have a right. So and they have to go at the same time, right? Have to go on the same time. So let's say left and right. L position equals self.m plus left, and the right position equals self.m plus right. So these are the leaves, right? And then left remove equals right remove equals to 0, right? Then we say while left position is not equal to right position, they are not merged into the same thing yet. Then we say on the left position, we're going to check, right, and say if left position is a right leaf, right, if it is right leaf, then left remove plus equal to, we're going to remove left self.sec3 left position minus 1, because I am in the right subtree, I'm the right subtree, and want to go up, so I need to remove the left subtree. Shouldn't that be hold on, let me think. So remove this and I'm gonna come here, right? And then we go up, and that happens to be another right? And then this one equals this plus this, right? So we're going to remove this, and we're going to remove the entirety of the left side. So on my side, remove this, on this side, remove the entirety of this. Yeah, I think I do have to remove everything, right? Otherwise, then if I am the left subtree on the left side, then I don't really remove anything. Same thing, if right position, I'm in the right position, but it's on the right, it's on the left, so equals 0. If not, right, then say right remove plus equal to self.sec3 right position plus 1, right? So we do this until we reach, and then left position equals 2, right position equals 2, so we go to the parent, and once we're done, and they're equal, so we exit, right, and they're equal, we exit, so we're going to return self.sec3, and they're equal, so we just say left position, right, minus left remove minus right remove. And I think these two we can do a little bit cheeky thing to put them together. So we have run 1 fewer lines to worry about. But that's some range. Let's make 3. Okay. A bit nervous. Console. Run the code. Let's see. List index out of a range. That is not correct. That is self.n. Run the code. What the actual hell? Minus? What? What is this? Oh my god. So it caused some range, right? Let's print. Right, let's print and self.setTree. Yeah, I know something's not right. All right, let's see. Okay, 135, right? And then we have 5 of 8, right? Times 2, 0, 1, 2, times 2 is 4. 4, yeah, is this. And then this one, 0, 1, 2, is this, 9. Why we have another 9? That's 9, 0 itself. Hold up. And the tree is not, doesn't look right to me. It should be 9, 4, 5, 1. Actually, the tree is not the same. Hold on. We have, that's 5 is here, 1, 3 is here, right? Then these gonna give us 4, and these will give us 9. Yeah, so it should be 9, 4, 5, 1, 3. 9, 4, 5, 1, 9, 4, 5, 9, 4, 5, 1, 3. That's 5. Yes, because 5, 6, 7, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that is, I think make tree has issues. The 0 base, 0, 1, 2, 3, 4, 5, 7. 1, 2, 3, 4, 5, 7. 1, 2, 3, 4, 5, 6, 7. A full tree, actually it should be minus 1, right? That's the full tree. And then we say n is 3, right? So 0, 0, 1, 2. Huh. The tree structure is different. I am confused. I am very confused. We say we fill up. No, I think it's different. The structure is different. Hold on, let me try it again. So we say we have leaf going to be 1, 3, and 5. That's the leaf side. And then we're going to construct the tree. We say from 1 up. So let's say this is what, 4, right? We have 3. What is 3? So it's 3, 3, 4, 5. 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. Yes. And then we say if we're looking at 2, right? 0, 1, 2. 2 has children 4 and 5. So actually 4 and 5. So we have 8 here. And then we have 1. 1 have children. 1 have children 2 and 3. But we don't have 2. No, that's 2. That's 2. It's 2. Right, that's 2. So we have a 1. Have a children. So it's going to be here. 9. That is not how I imagined to be. Wait, is that right? 0, 1, 2, 3 should be here. Hold on, hold on. No, I don't think so. This will become 1. This will become 1. The root is at 1. No, I want root to be 0. If root is 0, then I think 1, 3, and 5 should be 2, 3, 4. 2, 3, 4. And then we have 1. 1 needs to be 2, 3, right? So that gives us 4. And then 0. 0 needs oh, I think it's 1 based. It's 1 based. Because 0 base is harder to deal with. It's 1 based. I was very wrong. It's 1 based. Okay, it's 1 based. It's 1 based. That's 1, right? 2, 3, 4, 5. That is correct. And then I got confused in the construction part. It is 1 base segment tree, right? It's a binary tree, and left child. That's 1 based. That's 1 based. Let me see. We're from n. We go from n, so go from 3. If we go from 3, that's going to be 1. This is going to be 3. This is going to be 5. And then 2 is going to be 8. It's going to be 9. That's a very different segment tree. How do you justify it? It's like it's swapped, right? It's like it's swapped. Yeah, we move towards 1. I mean, it doesn't matter. So the segment is swapped, not left to right. It's right to left. Right? It's right to left. But it still works, right? It still works because we have the same, the left and the right subtree. So, okay, so what we're trying to say is this is correct because it's 1 based tree, right? And then that is also correct, right? And then it's not going to be, it's going to be to 0. It's going to be to 0 because we do not handle, this is going to be to 0, right? And say segment tree equals this. Alright, let's first just see if the tree builds up correct. This would be 98135. 98135. That is correct. Okay, that's good. And after update we get, well, we update 1. So 3 is updated to 2, right? So if I update to 2, that will be 7. So it's going to be 8, 7, 1, 2, 5. 8, 7, 1, 2, 5. That is correct as well. But in the update, we also should not go to the end and say, wow, this is larger than 0, right? Then do it. Once it becomes 0, actually, that should be actually larger than 1. If we don't change the first one. Yeah, we don't change the first one. Okay, these two are correct. Now we're going to handle the last part, the sum range. Okay, sum range is not correct. So the sum range, 0 to 2. So we find 0, which give us 3, that's this one, and 2, which give us 5. 0, 1, 2, 3. 0, 1, 2, 3, 4, 5. So 5 give us here, right? So remember the tree is swapped. The tree is swapped. Left and right is swapped. So now the left tree, the left part is actually on the right side. And the right part is on the left side. Oh man. How does this work? If you think about it, if we rotate it, right? We rotate it, but then that's still on the right side. So if I go up, if I want to include, then it has to be if the left side is actually the right subtree, then we can include. Otherwise, we cannot include. So I think what is going to happen is we just change this. The left, if the left, right? If the left is on the left position, or the left position is actually, it depends. It depends. It could be just because of this situation, the left and the right side. Right? If we do, say, 1, not 0 to 2, but 1 to 2, right? If 1 to 2, then they will be correct. Left is on the left side, right is on the right side. But if we do 0 to 2, we're looking at plus 3. It's 3 and 5. So left is 3, right is 5. So if left is 3, we know the left is the right child. 5 is also right child. So right and right, that's good. So we don't have to remove anything. So we just directly go up. We go to 8. Yeah, so I'll change this. So right child, then it doesn't do anything. So we go up, right? So we go up. What do we have when we go up? The right position go up. We want 2. Right, so right position now is 2. Right, so right position now is 2. The left position, how do I handle the left position? So the left position is a left child. The left position is a right child. So if the left position is a right child, as I do not include anything on my left, right? So I say on my side, I need to my position minus 1. So I need to remove 8. So I need to remove 8. So left remove is 8. And from 3, now we go to 1. Right, so we'll go to 9. And they're still not the same yet. And but one of them already reached the top. Sorry. One of them already reached the top. And the other one is not. Do we keep going? Now if I reach the top, if one side already reached the top, we just need to wait for the other side to reach the top. Everybody will reach the top, right? Everybody reaches the top, so I wait at the top. So if I reach the top, and I don't do any more. So the left removal is going to be 8. And for the right side, it's a left subchild, right? Which means it's 2, and we're gonna add its right position. So I say, well, it's gonna be 1. I'm gonna remove 1 and go up, and they both reach. So we have 9 total value. And then minus 8 minus 1, that gave us a 0. No, that's not correct. That is not correct. How do you query this range sum? That's 8, right? And then for me, I just include myself. I just include myself. Like value to add, right? Value to add. So like when I go up, because I am on the right side, so if I'm on the right side, a left child on the right side, I want to go up, I will accumulate the value of myself. If not, that will accumulate the value of my that I don't accumulate. Then the value will be the current parent. Right? Is that how it works? It's very counterintuitive. Go to the parent. Or, yeah, we can just do separate. Yeah, we just do separate. Don't do them at the same time. We just do separate until we reach the top, right? And then along the way, we're gonna add. We're gonna remove. Along the way, we're gonna remove. So on the right side, we're gonna remove 8. Then we reach the top. And on the left side, we're gonna remove 1. And we reach the top. Then when we reach the top, we know the amount that the left and the right has computed, and then we add both together. Maybe that is the way. Okay, so I have this. Let's just say while left position is larger than 0, right? No, actually larger than 1. Then we say if left position is a right child, then left remove plus equal to, yeah, it's going to be the same thing. I'm just going to remove this, and then left position equal to 2, right? And then we're going to do the right position as well. Right position larger than 1. Then if not this, we do this, and then right. So we do both. And then what we're going to return is secretary 1, so they both reach 1, times 2 minus this. Let's try this one. This one's correct. Do it there. Try it. Ugh, that is not correct. Alright, let's stop here. Let's check the solution. I don't know. It's very counterintuitive. Okay, update is fine. We got this. But this update is larger than 0. I mean, we have the same thing, right? Update. position, tree, and then doesn't matter. So this, if it's 0 here, if it's 0, right plus 1, else left minus 1, and then tree, I do this, position, yeah, okay. So it's the range. Let's see, get the left and right. Sum is 0, while left is smaller or equal to right. If left leaf is on the right side, then we do it itself. L plus plus. Hold on. If left is on the right if on the left is on the right branch, then I add myself, then I do left plus plus. What does left plus plus do? Left plus plus. We're moving to the left child of the adjacent subtree. Left plus plus. We add this, and then we, oh, that does make sense. Imagine a large bottom, and I am the left. I'm on the left range, but I'm on the right subtree. And what it's saying is we do not want to go up my parent, because my parent and all of its parents are not going to work. I am the odd one out. So I add myself, then I move on to the leftmost subtree, leftmost leaf that's belonging to the range. That's the left plus plus. And the right position is the same, right? The same. And then we go up. Holy moly, that is correct. Okay, so I'll do this. We don't need to do this. So the left or right, now we don't need to do the remove. We're going to say rest equals 0. And let's do this again. So we have while left position is smaller or equal to right position. Right? Left position is small. So they are trying to merge to meet each other. So allow them to meet each other. If that is the case, then we say if left position 2 is on the right side, then we say sum no rest plus equal to self.secTree left position, right? I'm the odd one out, and after that I'm moving. I escape, right? I'm going to the subtree within the range. Same thing from here. If right position is on the left side, then I add myself and going on to the left side. After all done, we go for our parents. So left position and right position, right? And eventually, I'm going to return rest, because eventually we will get to 1, right? If we merge, eventually we get to a position, and its value will be added one way or another. It will be added. Try again. It's correct. Submit it. It's faster. Okay, I think I have a lot to write about this one. I mean, I was on the right track, but okay, so this one is straightforward, right? I can say here, this is a very efficient way to set up segment tree. The intuition is that a segment tree is always a complete binary tree. Therefore, we can use an array as representation. The following is almost exactly a copy of the official solution. Copy the link for the official solution. Okay, so this one is easy to understand. We go bottom up. We first fill out the leaves, right? We first fill out the leaves. 2 times. Fill out the leaf. Wait, why is it 2 times? 2 times the number of leaves. If I have 2 leaves, we'll have 1, right? If I have 3 leaves, then it's going to be, I think it's 2 times n. Yeah, 2 times n minus 1 is the total number. Yeah, we fill out the leaves. Given n leaves, given n leaves in a complete binary tree, there are most 2 times n minus 1 nodes. What is a 4? Right? What is 1, 2, 3, 4, 5, 6, 7? 2 times 4 minus 1. Right? If it's 3, 2 times 3 minus 1. It's 5. 5 nodes. 1, 2, 3, 4, 5. Yeah, that's 5 nodes. I think it is 2 times n minus 1. If it's 2, 2 times 2 minus 1. If it's 1, 2 times 1 minus 1. Yeah, so there are not at most. There are 2 times n minus 1 total nodes. However, since we are using one-based addressing, we have to create 2n length array to hold the binary tree, to hold the tree. Yeah, so this is just, recall that in a one-based setting, a node at index I has left child at 2 times I and right child 2 times I minus plus 1. So this is fine. Update. This one is also simple, right? Update is also straightforward. We first locate the leaf by index plus n. Update that. Then we find its parent. To do so, we need to first check whether the leaf is a left or a right leaf. If it's a left leaf, then its sibling is index plus n plus 1. Otherwise, index plus n minus 1. After locating the sibling, we can go to the parent and update the parent by summing the values of the two leaves. That's fine. This is tricky. This is a bit tricky. We first locate the left and right leaves of the given bounds of the given bounds. If the left bound also the left leaf is also on the left branch, then everything is within range, and the sum can be represented by the parent directly. If the left bound is on the right branch, then the only thing that can be included is the left bound itself, and we must move the left bound inwards, right? We must move the bound inwards by doing left plus 1, such that we are within completely within bounds again. The same thing, right? The same thing happens to the right bound. Same happens to the right bounds. If the right bound is a left branch, is on left branch, we need to include the right bound itself and move the right bound leftward. Yeah, I should say not inward, but rightward, right? After handling the bounds, we go up to the parent for both left and right bounds. We terminate when left and right, when left is larger. Left bound is larger than right bound. Yep. Very good solution. Segment tree. Okay, that's it. That's it for today. I think there's nothing more to say here. Index tree, binary index tree. Yeah, that's binary index tree. Oh, that was simple. Some range, query this minus query this. Update. Oh, wow. He has updating here. Nah, Fenwick tree. Oh, I remember seeing this one. I remember seeing this one. Yeah, I remember seeing this one. Ah. I'm gonna give this a read. Maybe it'll help me even better to understand. But this is okay. Yep, that will be it. Yeah, I will give it a little bit of read later on. All right. See you guys tomorrow. Adios.